Good afternoon, everyone, and thanks for being here. I hope you will find this talk interesting. It's going to be more in-depth, and in particular, we will look a bit at database optimization and C# optimization, algorithm, this kind of stuff. So if these things interest you, you're in the right place. So for the people that didn't come to the other talk, my name is Marco Cecconi, and I am a developer in the core Q&A team at Stack Overflow. This talk is about one particular aspect of Stack Overflow, which is their tags. So how many of you are familiar with Stack Overflow tags? Yeah, about half, so I'll explain to everyone else. So Stack Overflow, of course, is a collection of questions with answers, but each question has up to five tags. So what is a tag? It's, maybe sometimes it's the language, like C# or Java. Sometimes it's the topic, like algorithm. So it can be a number of things. And tags are very important to Stack Overflow for a couple of reasons. First of all, after the first year of operation of Stack Overflow, the site became so big that it was impossible for any user to actually be proficient in all the kind of questions that were coming in. So the community specialized or split into different communities based on tags. So, for example, there was a C# community and a Java community and so on, and they look at the site by navigating the tags especially. So for example, if you're interested in C#, you can go in the C# homepage and see all the C# questions and not the Java questions. And this is obviously useful for a number of contributors. So this talk is about how we scale the performance of tags from the beginning until today. The latest things are things which are still in development and still not finished, so I can only give you some preliminary results. In particular, we are going to talk about scale, which is not that thing, but scale is basically like a beach. So, you know, you can have your code like a beautiful beach and there is no one there, right? And everything is nice and perfect and ideal, and you went to university and they told you the perfect way to landscape beaches and they told you to do this, right? And then one day you start working for a company and the company is successful and you realize that actually beaches are like this. So, of course, this talk is a bit an exercise in showing you how whatever can go wrong will go wrong, pretty much. So, talking about scaling, what does that mean? Well, it means that when you build a site, in the beginning, it's just you and your friends, right? 100 users. Everything goes. It's very, very easy. Up to 10,000 users, maybe, or 10,000 visits or whatever, it's more of a early product. So yes, you need to start considering maybe performance, but that doesn't really cross your mind all the time. And then, up to 100 million, it's a continuous ton of problems. So you're scaling up, you're scaling out, things change all the time, and you're sort of running around and trying to, you know, keep everything working all the time. And of course, over that, you need to ask Facebook people. I have literally no idea. So if you don't know how to even, by the way, there's that. So this talk is going to be a deep dive. So, again, what are tags? Tags are these little blue things here. Okay, this is an example question. You don't need to read it. Well, maybe you want to read that. What, do any of you know what Zardos is? Nobody knows? Do you want to know? No? Okay, it actually has a man in bikini in it. So it's a movie, but it's one of the memes of Stack Overflow is this guy here. It's actually a movie, okay? It's a serious movie. You shouldn't be laughing. Sorry. Okay, so we are saying tags. So we built this tool that handles tag queries. What are tag queries? So it can be something simple, like SQL Server. You know, give me all the newest questions, tagged SQL Server. That sounds very easy. Okay, let's make it a little bit more complicated. They can be Boolean queries. So I can say, give me all the JavaScript questions which are not also jQuery questions. So that starts to be a little bit more complicated, right? Then there are tags with wildcards, right? So users can look for questions which are about text that start with the string windows, but not necessarily only the string windows. So that is equivalent to this. And as you can imagine, you know, our users are very, very capable of inventing the weirdest queries all the time. So we need to find something in which this kind of queries takes an acceptable amount of time, even though we have 12 million questions to scan every time. So our mission. First of all, we have custom sorts. And you may think, who cares, right? A sort is just a sort. Not really, because first of all, you may or may not be scanning the whole set of questions. So if you want to sort based on some criteria, 12 million questions, that's a lot of work. It's just already, that is already taking way more than you want to spend probably. So it's not that simple. Then you want to get matches, right? But they can be on page n. So they can be page 1 in most cases, but in some cases, maybe it's page 42. And that is a known problem, right? Everybody finds it easier to find the first 10 matches, but not the matches 50 to 60. That's much more, usually takes much more time. We need to count the matches. So how many questions are there which are JavaScript but not jQuery? In order to do that, you need to scan the whole set. And then find related tags. So that means, given the criteria you have got, out of the result set, what are the other tags which are most prominent, right? So if you look for example, just for JavaScript, it's very likely that you will get jQuery as a related tag. So this is what our software needs to do. I encourage you to start thinking a bit about how you would do it. So the first thing that we thought, okay, so version 1 of the beach. First thing that we thought, SQL, right? So let's do this. So we have a table called posts, a table called tags, and a table called post tags. And it's a many-to-many relationship, right? And what do? Well, you need to find all the posts which have some tags, but not others, right? So for example, you can do this, right? Do you understand this code? So what it does is, takes the top 50 post IDs. We won't get the posts, we will get just the post IDs, and then we can hydrate them later. And then you need to do a join because you need to find the ones that have JavaScript and the ones that don't have jQuery, and then you need to join them. And then you have a sort. Right? So let me see if we can try this live. Otherwise, I just have the results, but it's more fun to do it live. So there is a site called data.stackexchange where everyone can go and run queries against our database. So you can try stuff there. Okay, so for example, I can just go to one that I created before. There you go. So this is the same query as there. If I run it and I look at the messages, it will tell you things like this, right? So look at that. It's reading all the posts and logical reads, 2,000 reads on the post tags, right? In practice, what this is telling you is that you will see, your user will see 1 second elapse there, but the CPU is actually putting in 3 seconds of work. And that means that basically 3 CPUs are working 100%. It may be split differently, but it's a lot of work. And honestly, our idea of, so this stuff maybe powers the home page. So we want the home page to be under 50 milliseconds. 50 milliseconds, not 3 seconds. So no, this doesn't really work for us. So it can get even worse, right? Because, hey, this is just getting the top 50. And maybe it's hitting, actually, it is hitting an index in order to sort, and it doesn't have to sort. But if you want to get to the top 10 related tags, the only way you can do that is by scanning the whole table. So this is a query that does that, is similar as before. So it finds all the inner part here, finds all the questions which have those criteria, and then what it's doing, instead of returning the IDs, is returning the top tags in the result set. And this is, of course, has the effect of forcing everything to scan through, and the query is going to be equally bad. So these are the top 10. And as you can see, it's counting a lot of stuff, yeah? And the results are a bit worse, right? So yes, it takes only 740 milliseconds for the user, but for the CPU, it's 10 seconds. So we are basically pegging SQL Server for 740 milliseconds, which is outrageous. So you can't really get much performance out there. And of course, we still haven't got all the things that we needed to do, right? So this is one example in which something is an easy sort, right? Some of our sorts are actually very nasty. So we have a hotness sort, which is similar to maybe the homepage of a Hacker News or the homepage of Reddit, where you find based on activity and votes, you find the top questions. And that, of course, is a sort which is time dependent, and it includes logarithms and stuff per row. So that's terrible. So yeah, this worked in the beginning, but just in the beginning, really. Can't do that. But we wanted to keep using SQL Server. Right, so new version of the beach. So, who of you knows full text search? Yeah, about half. Well, for the others, it's a very simple, well, not simple at all, but it's a very in simple terms, it's a technology which you can enable on SQL Server, which makes it a little bit like a Elasticsearch. So what it does, it reads the fields for which you enable full text search, and it breaks them up into the keywords which make it up, and it's able to, for example, return all the rows which contain the word, I don't know, foo or SQL. So it's basically an index based on the content of text, and which also understands the way text is put in, so it understands like languages. It knows how to strip away, for example, full stops. So, hack. We denormalized the tags and put them on posts. So, first of all, you don't need, so if there are maybe 5 tags per post, you have 5 times more rows than posts in your many-to-many table. But if you denormalize it and denormalize the tags in the post table, you only have 1 row per post. So if you can do that and put all your tags into a string, you can maybe ideally do queries like this, right? Use contains, which is the keyword to use full text search. So, and you tell it, okay, tags contains JavaScript and not jQuery. And all the work is done by full text search. Isn't that great? It's a fantastic hack, which we put together and actually lasted for 3 or 4 years. So never undervalue the power of hacking. Right? Except I cannot show it to you here because we don't have it enabled anymore in the data.stackexchange site. But as you can see, it still has some problems. It's much better for complex queries, right? I've shown you just JavaScript and not jQuery, which is fairly simple. But if you remember, there was the Windows one with 20 terms. How do you do that in SQL? You do 20 joins? Good luck. But you can do that here. With this kind of code, you know, that kind of 20 terms become just a longer string in here. And all the work is done by the indexing engine, so it's still relatively fast. Of course, as our numbers increased, as you can see, this was not good enough. Also, it was a hack. And hacks are rabbit holes. You know, they start great, but then, for example, yes, we are using a full text engine to look for tags, but tags can contain numbers, so they can contain I don't know, hyphens, right? So we can't have tags which contain sharp, for example. And how do you do with C#? Okay, you hack them, right? So C# becomes C cedilla, and you know all the hyphens become something different. So you need to translate them, put them in, and translate them back. And it works, but it's pretty ugly. Then you can't really do stuff like AND and OR. You can have tags like that. Because they are stop words, right? So full text engines ignore some words because they match too many things. So they're hard-coded not to index AND OR. And so we couldn't allow them as tags. Also, we had a problem in which full text engine would strip like the end or the beginning of a word because it was optimizing to do full text search, which is normally of text. And if, let's say, if you look for, let me see, for school, right, it's going to match school, but it's also going to match schools. And it's also going to match schooling. So what it's actually storing is the root of the word that it finds. So it's only going to store inside its index school. And therefore, you know, if a tag ended in ing, it would strip away the ending and it wouldn't match correctly. So we needed to pad all the tags with random letters. By the way, we are using these letters not because they're funny, but because we thought, hey, nobody will never need them, right? Because who cares, right? This is only English. Except then we opened Stack Overflow in Portuguese. That was fun. So basically we started having stuff like this, right? So that's .NET and C dot, I think. Or C sharp, who knows? Yeah. So it was a great hack, but so at some point we decided, okay, this is really ugly. And B is not really scaling. So we need to find something better. So what did we do? Hey, index all the things. So how does that work? Well, we use reverse indices, okay? So you have one index for C sharp, which is the index of all the questions that contain C sharp, and then an index of all the questions that contain Java and so on. So using reverse indexes in memory, something that you don't do in SQL, is something that you do in memory, is a specialized collection of indices which you can query very, very fast, right? If you ask me, okay, give me the top 10 questions with C sharp, hey, I can just look them up in the index. And, you know, literally I need to give you the first 10 I find. And if you are asking me how many are there, I can just give you the length of the index. Or, you know, or 0. So it's really good. Yeah, so this is the idea. So keep a list of all the questions. And we want to limit the amount of data because, again, 12 million questions, you don't want to keep them all in memory. So we just keep the IDs and the data which we use to sort on. Right? So, for example, if we sort by date, we need to sort the date. If we sort by last activity date, we need to include that. If we want to sort by score, we need to sort the score and so on. And then use sub-indices, right? So sorting is generally too slow. So if you want to have 5 different ways in which you can return, 5 different sorts in which you can return the C sharp questions, you are going to have 5 indices all sorted in different ways. So it's a lot of memory. We are trading off a lot of memory to get a lot of speed. So Tag Engine was born. And it was really, really good, right? So it came out and each query took 1 millisecond. And which was really, really good, yeah? We were running like maybe into a second before with SQL Server. Except things are not so simple, right? Because right now, this is the solution that you would get out of, say, university. You would say, okay, you do these indexes, nice algorithm, it's going to work. Yes. In the real world, it doesn't. And it doesn't because when we look at the response time, we saw things like this, right? So, explaining a bit. This is time, like Monday, Tuesday, Wednesday, or 1 hour. And this is the response time. So how long it takes to get an answer out, or a page out. So what are these? Right? These are moments in which the response time goes from maybe, I don't know, milliseconds here to seconds here. What's happening there? Well, what's happening there is that we are garbage collecting. That's what's happening. Why? Because we are keeping a gazillion objects in memory, right? These indices are huge amounts of objects which are we never touch. They are long-lived objects that stay in memory all the time. However, when you garbage collect, you need to scan them because they are keeping alive. So the list is keeping alive all the items inside. So that's a scan that needs to happen during garbage collection, and it's a nasty garbage collection. Also, we did, I think that gives the idea. That was a blog post. So we started using, we did two things. So the first thing we did is we split up this code into a separate machine. So here was born Tag Engine as a separate server. So at least if there were performance spikes, they would only be on a separate machine and they would not affect all the answers, just the ones in which they were touching. But then we still had the problem of the garbage collection spikes. So a few tricks that we did. And most of them, I don't think they came from game programming, but they are very similar to what is done in game programming, so I'm just going to call it. So first of all, if you have one thing that we had is a list of posts, as I was telling you. So what does this do? Well, first of all, the space which is allocated is dynamically allocated, right? So it can expand or contract, but we never use that, and we don't want really to allocate all the space or extra space just in case. We also don't want really to leave up to the runtime to decide when it's time to say, maybe move around that bit of memory, because it's a lot of memory. It takes significant time to move. So, and also it's a list of objects. So in practice, you're storing a list of pointers, and therefore you still have the problem of scanning through all the pointers, because pointers is what the garbage collector does. It says, okay, this is a list of posts, and then I'm going to scan it and mark all the objects which are pointed to as alive. And that takes time. So first of all, we went to an array of posts. So this means that the space is fixed, and the compiler can optimize for space that never changes in size. And then post became a struct. And a struct can be embedded inside the array instead of being a pointer. And this, of course, is great because it avoids that garbage collection issue. But more. So as I was telling you, the post, of course, has a list of tags inside. The problem is that even if post is a struct, it's going to be treated as an object the moment it has some variable size, right? The compiler doesn't know how to allocate the same size for everyone. We know that we have at most 5 tags. However, the compiler does not know that because it's not declared anywhere. So it's going to make these structs behave like objects, and so the trick before won't work. So we created a fixed size array, right? It's a bit hacky. It wastes a little bit of memory because in some cases you won't have 5 tags. However, it guarantees the size and it guarantees the structure. More, the indexes are interarrays for the same reason. And we use them a little bit like pointers. They're not pointers, but they're indices inside an array. We use fixed for both. Fixed is a keyword that very few use, but allows you to prevent the garbage collector from moving memory around. So when garbage collection happens, one thing that the garbage collector tries to do is compact memory. Right? You want to have memory which is used memory which is compacted together, so you have big blocks of free memory in case you need to allocate big objects. And of course, we don't really want that to happen here. So a lot of tricks went into that code. So how do we scan though? So how do we write the code that does the scans on top of these indices? Well, the first thing one would think is like just use link to objects, right? Not really, because when you use link to objects, and in general, when you use link, you're creating stuff which depends not only on closures, but sometimes depends on immutable objects. So every time you do a select, you are going to create a new instance which contains only the data you want. Maybe you're going to create a tuple or something like that. You don't really want to do that every element of a scan, right? You're creating a huge amount, millions and millions of objects just because of that. So can't really do that. So it's back to old C-style code. For loops and, you know, ints. And that's all it is. So this is actually the code of the inner loop. And what does it do? It has a matcher class here. And the matcher class decides whether a post in the index is actually part of our result set or not. So you may check whether a question is closed because maybe you want only non-closed questions, or whether it's upvoted because maybe you just want upvoted questions and so on. So it's a complex matching class. If it is, it increments the count and then it stops at 51 because we just want to return 50. And of course, we still need to scan for the rest of things to count the related tags. Right, so how do we optimize that? Because, hey, this is scanning 10,000 rows, so it's not fast. So just go parallel, right? Not as simple. So let me explain why. This is a bit complicated. So this is the tag engine, okay? Tag engine here, the hardware here, and these are the incoming requests. So we have a bunch of requests coming all the time. So the way we built it a bit like a web server. So how does that work? It means that this layer up here is going to respond as fast as possible to all the requests in parallel, and then dispatch each one to get an answer on his own thread. So from the point of view of the thread, we are basically single-threaded, but there is a top layer which is multi-threaded, which is how web servers work. Right, so all the requests are passed together, each one is slightly different time, and then as they arrive, we need to serve them. But of course, we can't use all the cores for all the requests, because otherwise we're going to stall the other requests, right? So we can use at most 2 cores, right? So as they are served and as one is running, we still have some free space, so we are not making all the requests waiting for a core to be available, right? So from here to here, the first one ends, and then the new one comes in, and so on. So we have many concurrent queries and few cores, right? So it's not trivial, or it's not obvious that this is true. We needed to measure it, and we needed to find how many degrees of parallelism we could put in order to have the best performance, right? And out of that measure, we determined that with our own load and with the time it takes for us to actually serve each request, 2 threads was the best compromise. Unfortunately, though, it was better, but not substantially better. So it was almost twice as fast. That's all. But still, we were maybe in the order of seconds and not in the order of milliseconds. Right? So, new tricks. Right? So, let's talk about code that writes itself. So, back to this. So, what did we do here? Well, we pulled out a profiler, pulled out some load from the actual site, the actual Stack Overflow site, and try to play it in the profiler. What came out is that most of the time we were spending here, this line here, right, in this if. So the reason for that is, well, there is really no reason. So this is the matcher. This is how it worked. So what does it do? The top part here is initialized when you create the objects, right? So once per query, you create this matcher, which represents your query. So if the matcher needs to return non-closed only answers, you're going to set it at the beginning, once you interpret the query that you're receiving. And then when it runs this part here, right? So if I set it at the beginning, this is going to be true, non-closed only. So it's going to go in here, and then it's going to make the check. And if the check fails, it's going to return false. As you can see, it's not complicated code. It's actually very trivial code, and it's very fast code, right? It is, except, you know, for a query, you don't need to do all these checks. Most of the times, you're just using a few of those. So what you could do is to create a set of classes, each one having the right combination of filters, so you're actually writing less lines of code, or you can write code that creates these classes for you. And this is what we did. Instead of having a matcher, we have created an iMatcher class interface. And then we have a matcher generator. And then what that does is, this is all at compile time, okay? Sorry, this is all at when the query is compiled, so when you receive the query but is not executed during the scan, it creates, so this emits here. What they do is they emit intermediate language, they create intermediate language, which then becomes a func, and then the func is run during the scan, right? In this way, we have created the minimum amount of instructions that we need to run in order to be able to do the scan. And this actually worked. And then we've had good results. But, I mean, you may think, okay, we are crazy, right? I mean, who does this? Well, we do. But it's very tedious and very complicated to write this code. However, it is significant. So you may object, okay, but we can just approximate, right? Because a lot of time is spent just trying to look at how many results are there, for example. Right? Why? Why are we doing that? Well, you can't just approximate, right? Because there are things in which the top matches are never going to be representative by design of the rest of the scan, right? So, for example, let's say you're looking for questions with bounties. Bounties is a property of questions. It means that the user is giving a little bit of their reputation to the answerer in order to get an answer. So we want to find questions which have this property sorted by newest. And so we can't really use the first matches as a representation of the whole index. And the reason is that bounties are time-based. So bounties are only going to be in new questions. So you're going to find all the matches in the beginning, but there are no matches in the rest. So maybe in the first 1,000 or 1 million questions, you find your 50 matches, but there are no more matches after that. So you're going to return that there are 600 questions with bounties, but in reality there are only 50. So approximating does not work at all. Just put them in MongoDB, right? It's web scale, right? Okay, so that worked, but it's still really not fast enough. So now we're going into the more experimental territory here. So one thing that we started doing, and this is just an example, an experimental homepage we put together in which you have this top search bar in which you can put in tags, and it's going to search by tags. As you populate this top label, the results under it are going to change in real time. Right? So you write Git and you get all the Git questions. Then when you write Git and JavaScript, you will get Git and JavaScript questions, and you want that to happen fluently as someone types, a bit like Google. Also, there is this side here in which you return other things, like, for example, how many questions are there that match. So the way we made this faster is not only doing all those tricks, like, for example, self-writing code, but we started splitting the queries in two parts, in which in one part returns just the results, so you can stop at 50, and then the other part does the scan and returns asynchronously the result to the page. So the page populates in 2 times. So the preliminary results there of these things, we almost, we almost half the time in the worst case, and a lot of hits went under 100 milliseconds. So it's a very significant performance improvements. Remember, 11 seconds, the worst case when we started before. But then again, this was not enough, because 700 milliseconds is still too slow. We want to go under 50 milliseconds. So we started to rethink the tag engine. So what if we don't make it behave like a web server, but we make it behave differently? So when you receive these 8 calls, only one goes through. The others wait, and the one that goes through uses 8 cores. And then another one goes through and uses 8 cores. So we make them wait at the beginning, but then we can use maximum parallelism in order to do it faster. Because if you think about the index scan that we are doing, it's something which is really, really easy to parallelize. Right? It's just a for loop over 12 million independent rows. You 2 cores, you just split it in 2. With 20 cores, you split it in 20. And that's it. And then you can, it's very trivial to put together everything. So that would be great. And this is what we built, and actually started to perform better. But then, not only it performed better, but it performed so much better, then we started thinking a bit more wild. Right? What if we started using GPU cores? Right? So, because, you see, one of the problems there is that if your scan is very, very fast, it's okay. You can give a lot of work to each of your 8 cores, 1/8 of the work, and then it's going to be fast. But if the scan is slow because it's complex, then the fact that you're dividing just by 8 cores is going to be a problem, because still 1/8 of the work is slow. So with GPU cores, we could actually make it run the complicated ones, right? So this is how we built it. So basically, if you're making a simple query, it will be going in the normal CPU cores, but in the other case, it goes through all of them. And actually, we could add another layer of parallelism in case in which we got 2 queries, one which is simple and the other one which is complex. Or in case which are both simple, actually, we can just push them through, one to the CPU cores and one to the GPU code. And this furthermore increases performance. So these are some benchmarks. This is the really, really cutting edge stuff. So this is the version 1 of the tag engine, zero GPUs. So on average, we were running 52 milliseconds per query. And the new version, this is just CPU, 3 milliseconds. And this is the number of GPUs. So you can actually buy machines that have different CPUs. So each one has like, I don't know, thousands of cores. And these are the times. So 1 millisecond and so on. These are complex queries, by the way. So most of these things, by the way, I didn't write. Okay, so this guy, Mark Gravel, is fantastic project lead on this. He has written in depth about how this was done. So if you're interested in the really hardcore CUDA parts and so on, he is very open about them, and they're available on his blog there, or just look for Mark Gravel. So the moral of the story, since time is almost up. First of all, measure everything. We would have used parallelism in the wrong way if we didn't measure. We would have never gotten here if we didn't know that the website was garbage collecting all the time. Measurement is fundamental in order to get results. Don't assume stuff, right? It's obvious, right? More parallelism or MongoDB, right? Obvious. No, it's not obvious. So, canned results or canned answers are generally wrong. When you try to do something that nobody has done before, and I am pretty sure that nobody had a Q&A site with tags before Stack Overflow, there are no canned answers that are going to work. You need to think with an open mind to the solution. Also, you need to keep on evolving. You're not done. You have not put together the fantastic hack with a full text index, and then you're done. No, you need to evolve. Okay, quick plug, completely different thing. So the talk is over, but I just wanted to tell, we are giving out this badge today. Okay, this is a Stack Overflow badge. You can get it on your Stack Overflow profile. You can only get it here. We do it just over people that come talk to us. So go grab it. It's either from me or from a table. And I think that's it. Thank you very much.
Thank you, Marco.